So I wanted to go through some problems, give you a little bit more of an idea so you can work on these as you're at home, getting some practice ready for that test. We're going to go over to some of these problems, and I'm not going to solve them completely, but I'm going to give you some guidance on how to solve them. Going over some things that you may have forgotten from before the break, anything like that. We'll also talk a bit about it on Wednesday. All right, problem number 5. It says find the complete solution of the system. You might think that's like these problems up here, and you're definitely right, it is. One of the things that this does is make sure you understand that a matrix can include zeros if those variables are not located. So just looking at this, you might quickly jump to the idea that this is a matrix that looks like this. 1, 1, 3, 1, 2, 1, -1, 1, 1. And it definitely does look like that's the truth. I mean, you got the numbers right there. But those numbers don't actually match up in the variable category. The z's do match up, so that's kind of nice. But here we've got the x and the y's. Those do not match up. So that's something that you need to pay attention to. When you're solving a system of equations, the x's, the y's, and the z's are separate terms. And in a matrix, they have to be in separate positions. So if I look, the only x is in the first row, or in the first row, so we put 1, 0, 0. There's no x's in row 2 or row 3, but there are y's. There's no y in row 1, but in row 2 there's 1, in row 3 there's -1. And so our equation should look like this. Now, once you have, our matrix should look like this. Once you have this, then you could go through the process of solving the rest of it. But you do want to make sure that you understand the difference between the x's, the y's, and how we organize the variables. One of the things that I like to do during class was actually write them right above it. And that's something you could do too, to keep track of it. Again, not only am I here to teach you this, but to give you some good strategies to solve it. An important thing for you to remember is the basic idea. Each column represents a specific variable, whether you write it down or not. All right, so that's solving a system of equations. It's stuff we did and stuff we can continue to do in class on Wednesday. But what about some other things we do with matrices? Matrices, again, they are like numbers in a lot of different ways. There's some ways they're not like numbers, but they are a combination of numbers or they include a combination of different numbers inside them. Those numbers are called elements. So 3 is an element of the matrix A. -1 is, 2 is, and that 2 is. And specifically their location is pretty important. So what can we do with these matrices? Well, we can combine them, add them, subtract them, multiply them, etc. And here we want to multiply these two matrices, multiply A and B. So if I'm going to multiply AB, first thing to do, good thing to do would be to write it 3, -1, 2, 2, and 2, 3, -1, and 5. Oftentimes, when we talk about multiplying, we do put an X there to say multiply these matrices. Whenever you're talking about a dot, and you're getting into things like matrices and vectors and things like that, you're thinking of a dot product. And so an X talks about multiplying them. All right. Whenever we multiply matrices, an important thing to remember is that we multiply the rows times the columns. And if you notice, there are 2 elements in the row here, and those have to be multiplied by the 2 elements in the columns there. And if you think about the way that matrices are written, we've got lines by columns, or rows by columns, and so the number of rows tell you how many columns there are, and the number of columns tell you how many rows there are. Tell you how many are in each row. So there are 2 elements in each row because there are 2 columns, and there are 2 elements in each column because there are because there's 2 rows. So knowing that if these match, if those 2 values match, then we can multiply them, and we can do it right here. 3 times 2 is 6. Negative 1 times negative 1 is 1. Okay, and then whenever we do the second one, we need to multiply the first row by the second column now. So that's 3 times 3 is 3. 1 times negative 1 times 5 is negative 5. So that's 9 minus 5. Okay, then we would do the same thing with the second row times the first and second columns. That's 2 times 2 is 4. And 2 times negative 1 is negative 2. So that's 4 minus 2. And last but not least, 2 times 3 is 6. Plus 2 times 5 is 10. And then we just need to add them to get a solid, nice number. 7, 4, 2, and 16. Whenever we multiply them together, that's what we end up getting. All right, with that said, that's a pretty simple process for multiplying them. I'm not really going to go through the rest of this section too much, other than to say whenever we have a constant that's multiplied by our matrix, we need to make sure it multiplies by every element in that matrix. It's kind of like distribution for regular numbers. So this is 2b, so it would be 2 times the whole matrix, which is 2, 3, negative 1, and 5. Okay, so that leads us to a new matrix that is 4, 6, negative 2, and 10. Okay, it multiplies by every element, not just each row or one element, each row or each column or anything like that. Every place. All right, so you want to finish up C. C is not done. Not done. You need to finish C. Okay, D is nice in that you see, oh, if I've solved for a matrix, I've got to solve for everything. And just so you know, X is a 2 by 2 matrix. I would usually use the letters A, B, C, and D to describe it. You need to actually find out what all 4 of those are by solving that equation. Okay? And then here you want to solve for A and B. You don't need to come up with a matrix answer like you would for the previous one. You do just want to come up with equations that allow you to find the value of A and to find the value of B. All right, and then we go on to inverses and determinants. If you remember, a determinant helps determine some things about the matrix. If the determinant is 0, then the matrix does not have an inverse. But if it's not 0, the matrix does have an inverse. And for problem number 8, I am going to go through this whole problem real quick. First, it says find the determinant of that matrix. Okay. So we want to find the determinant of that matrix, 1/3 15, 4/3 9. Well, DET is how we would use the determinant, and inside we would just put the name of the matrix. This matrix hasn't given us a name yet, so we're going to call it matrix A. So the determinant of matrix A, and that is equal to a solid number that is A times D, or the first one times the last one, those, and then we subtract this one times this one, okay? To get the determinant, that's how we do it. So it's 1/3 times 9 minus 15 times 4/3. Now, going through that, 1/3 of 9 is 3 minus 15 times 4/3. The 15 and the 3 can cancel, and we end up with 5 times 4, which is 20. 3 minus 20 is negative 17. All right, so now we know what the determinant of A is. The determinant is not equal to 0. So A has an inverse. Now there is a shortcut to find an inverse of this 2 by 2 matrix. But I don't really like to use the shortcuts because, again, they only work for certain ones. It's better if you understand the entire idea here. And if we want to find an inverse of any matrix, no matter its size, what we have to do is just make it augmented with the identity matrix of its size. Since A is a 2 by 2, the identity matrix is going to be a 2. And we end up with this. Let me make sure I've got this. 1/3, 15, 4/3, and 9. Is that correct? Yep. Then it's in the identity matrix is 1, 0, 0, 1. Looks just like that. All right. So if I want to solve this, or not solve this matrix, if I want to get the inverse, my goal is to turn A into the identity matrix, and whatever the identity matrix augment becomes, that will be the inverse matrix. So I'm going to just go through the process here. This one I'm going to do very quickly, not really explain my actions, because I don't want to run out of time. So we're going to add row 1 to row 2, multiplying it by -4. That'll get rid of the 4/3. We end up with 1/3, 15, 1, and 0. On the top, on the bottom, we'll end up with 0. And 15 times -4 is -60, minus 9, plus 9, which is -51. And -4 times 1 is -4, plus 0 is -4, and okay. So we just added row 1 to row 2. Now if I look at this, I just got to do a few more things. One of the things we'll do is first I'm going to multiply row 1 by 3. And that'll turn the 1/3 into 3, or into 1. And I'm also going to multiply row 2 by -1 over 51. That'll get rid of the -51, turn it into a +1. By doing so, I end up with 145 and 3, 0. Okay. On my second column, I get 0, 1. That's nice. This one becomes a little weird. -451. Okay, or +451st. And -151st. All right. Not too bad. Now I need to multiply. Is it 4? Huh. For some reason I got, I just wanted to make sure. Yeah. Okay. Multiply row, or add row 2 to row 1 after multiplying it by 45. So I'm going to say this, add row 2 to row 1, multiplying it by 45. -45, and that's going to cancel out the 45. So I do end up with the identity matrix, 1, 0, 0, 1 on one side, but the other side becomes a little bit stranger. Is that a fire?